Hi everyone, today we're going to talk about graphing radical functions, but first please pause the video and give this warm-up a try where you're going to be making the parent function for our square root and cube root functions. All right, go ahead and check your work. So you'll notice for the square root function, for the x values, I didn't pick any negative values because you can't take the square root of a negative. There's no real number for that. And you'll also notice that the x values I picked are all perfect squares, making it easier for me to plot the points on my graph. So this is the general shape of our square root function. And notice that it does have an endpoint. It stops here and then it kind of increases going over to the right. For our cube root function, notice that I did include negative numbers here because you can take the cube root of a negative number. And also notice that I picked all perfect cubes. 8 and 1 are both perfect cubes, whether they're positive or negative. So you get a graph that looks kind of like this. So the right side looks similar to our square root function, but because you can take the cube root of a negative, you see this region down here that our square root function does not have. So again, what you just made are the parent functions for square root and cube root functions. So our parent functions are listed here again. So for our square root functions, these functions do have a restricted domain and range. It has a restricted domain because you can't take the square root of a negative number. So our domain is x is greater than or equal to 0, or if you're doing that in interval notation, it would look like this. Bracket and then 0 to infinity. And the range is actually the same. It's everything greater than or equal to 0. So bracket 0 to infinity. Now, for our cube root function, the domain and range are actually all real numbers because you can take the cube root of a negative number and it will reach all y values possible as well. So for our domain and range, it's all real numbers, which in interval notation, remember, is negative infinity to positive infinity. So today we're going to be graphing these functions, but we're going to be starting with the parent functions and then using transformations to help us transform our coordinates. So here's a review of all of the transformations that we've learned. And you can see that we have what it looks like in function notation, what it looks like with our radical, what it does to our graph, and then what we would do to our t-chart. So let's look at our translations first. Remember, if we're adding or subtracting from x specifically, so in this case it will be inside the radical, it's going to shift your graph to the left or right, and it's going to move in the opposite direction. So if you subtract 2, it actually goes 2 units to the right. If you add 3, it goes 3 units to the left. So remember, with the x, it moves in the opposite direction. So what would you do in your t-chart? Well, if you want to go 2 units to the right, you add 2 to x. If you want to go 3 units to the left, you subtract 3 from x. Now here, remember, if you're adding or subtracting to the entire function or not specifically to x, that's going to be a vertical translation. So it's going to shift up or down. And so you would add or subtract from y in order to do that. If you are multiplying by negative, it's going to be a reflection. So multiplying to the x specifically reflects over the y-axis. And multiplying to the y value or to your entire function reflects you over the x-axis. And to do those reflections in your t-chart, you would simply either multiply x by -1 or y by -1, depending on the type of reflection. So this one here is a horizontal reflection since it's affecting x. This one's a vertical reflection because it's not specifically affecting x. And then we talked about horizontal stretches or shrinks. This was the tricky one. So these, I'm going to maybe highlight it because that stretch or shrink factor had that special rule where the factor is the reciprocal of what you see. So if you're multiplying x by 3, it's actually a horizontal shrink by a factor of 1 over 3. And if you're multiplying x by 1/2, well, the reciprocal of that is 2, so it's actually a stretch by a factor of 2. So if you're doing your t-chart rules, you're going to multiply by whatever the factor is. So you're not multiplying by what you see in the equation, you're multiplying x by what your stretch or shrink factor is. And then the last one, if you see that you're multiplying the entire radical by some constant, that's a vertical stretch or shrink. So it's a stretch if that number is bigger than 1, and it's a shrink if that number is between 0 and 1. And remember, our stretch or shrink will never be negative. That would be a different type of transformation. It'd be a reflection. So we always consider the a value to be positive when we're doing transformations. And you'd simply multiply y by whatever that stretch or shrink factor is. So hopefully this looks familiar, because we did the same process with absolute value functions, then we did it again with quadratic functions. So now the only thing that's new is we're starting with different parent function coordinates, which you just made in the warm-up. All right, let's give one of these a try. First, we're going to describe the transformations to get that extra practice. Then we'll make the t-chart for our parent function, and then we'll transform those coordinates and graph. So if you look at what we have here, one thing I see is I'm adding 3 to x. So I know that that's a horizontal translation, and it moves in the opposite direction. Anything with x is opposite, so it's going to go to the left 3. And then I see one more transformation here. I see I'm subtracting 5 outside of the radical, which makes it vertical. So it's a vertical translation, and this one's just going to go down 5. So before I transform my coordinates, I need the parent function coordinates. So in this case, we can see that our parent function is just square root of x. So you'll see that I picked the x values that are all perfect squares. So the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, and the square root of 9 is 3. So for square root functions, we'll always start with these 4 coordinates. Now if you want to shift your graph to the left 3, you're going to subtract 3 from x. And if you want to shift your graph down 5, you're going to subtract 5 from your y value. Or I'll write p of x because it's the y value of your parent function. So maybe we'll say p of x minus 5. So then again, I'm going to take these x values and subtract 3 from all of them. So negative 3, and then I have negative 2, positive 1, and 6. And then I'm going to take all of the y values from my parent function, and I'm going to subtract 5. So negative 5, negative 4, negative 3, and negative 2. And now all I need to do is plot those coordinates. So I have negative 3, negative 5, negative 2, negative 4, 1, negative 3, and 6, negative 2. And it is important that we make our graph, we have these coordinates, but there's lots of ways that you could connect them in the wrong way. So here it might be nice to remember what our parent function looks like. So our parent function looks like this. So we need it to be that same general shape, but shifted down and to the left. So our new function should look like this. So again, make sure it doesn't go past this point here, and then it's going to continue on to the right. So from this, we can see that our domain has also been shifted to the left 3. So our domain is going to be negative 3 to infinity, and our range has been shifted down 5. So our range is negative 5 to infinity. There you go. So again, it's super important that we know how to find our parent function coordinates, and then if you know your rules of transformations, which we've already done for 2 different types of functions, it should be easy enough to transform those coordinates. All right, let's try another one together. So here I have another square root function. Let's describe the transformations we see. I see a negative out front, so I know that that's a reflection over the x-axis, which is actually a vertical reflection because I'm going top to bottom or vice versa. So even though it's over the x-axis, that is a vertical reflection. The next thing I see is I'm multiplying by 2 out front, so that's going to be a vertical, and that's going to be a stretch because the factor is 2. So by a factor of 2. Then the last thing I see is that I'm subtracting 1 from x. So since it's specifically grouped with x, it's going to be horizontal, and it's a translation because I'm adding or subtracting. This should go in the opposite direction. So it's going to go right 1. So again, my parent function I can see should be the square root function. So we'll use those same coordinates from before. And then the only horizontal change I have is going to the right one. So I'm going to add 1 to x. And then I have these two vertical changes. I have the reflection and the stretch. So I'm going to multiply the y values from my parent function by -2. So let's start with the x values. Again, I'm taking the x values from my parent function and I'm adding 1. And then I'm taking the y values from my parent function and I'm multiplying by -2. So 0 stays the same. Then we have -2, -4, and -6. And then let's plot these points and see what it looks like. So we have 1, 0, 2, -2, 5, -4, and 10, -6. So we need to make sure we're connecting these in the right order. Again, it may be nice to go back and revisit or even draw in what our parent function looks like. So this point is now this point. So this is going to be our starting point, and then it connects to this point, which is this one. So because it's been reflected over the x-axis, instead of increasing, we're going to have a decreasing graph, but it's still going to head off to the right. So it's going to look like this. So you can see that our graph has definitely been reflected. It's been shifted to the right one, and it is definitely growing a little bit faster vertically than our parent function, which is why it looks a little bit more stretched out. So that's that vertical stretch by a factor of 2. And then for our domain and range, we can see that our domain has been shifted to the right one. So it's 1 to infinity. And then our range, because it's reflected, remember we always go low to high. The lowest y value is going to be -infinity. It's going down forever. And the highest y value is going to be 0. So now it's -infinity to 0. So you need to be careful with the range when you have that vertical reflection. All right, let's try one more together, and then you can try one on your own. So first I see that I am multiplying by 1/2 in front, which makes it a vertical stretch or shrink. Now because that factor is less than 1, it's going to be a vertical shrink. So by a factor of 1/2. And the next thing I see is the negative on the inside, making it a horizontal reflection. And if it's a horizontal reflection, it's going to be a reflection over the y-axis, because it reflects it from the right side to the left side or left side to right side, depending on where your graph starts. So it is a horizontal reflection, but it's a reflection over the y-axis. And then here I can see that I'm adding 5 on the outside. So it's outside of my radical, which makes it vertical. I'm adding, so it's a translation, and it should just go up 5 units. So again, my parent function is a square root function. We will do a cube root function in just a second. So our parent function coordinates are right here. The only horizontal change we have is that reflection, so it's going to become -x. And then we have 2 vertical transformations. We have the 1/2, so we're going to do 1/2 times p of x, which is the y values for my parent function, and then I'm going to add 5 after. So for my x values again, multiply them all by -1. And for my y values, I'm going to multiply them by 1/2 and then add 5. So I have 0 plus 5, which is 5. I have 1/2 plus 10 halves, which will be 11 halves. Here, 1/2 times 2 is 1, plus 5 is 6. And then here, 3 times 1/2 is 3 halves. The 3 halves plus 10 halves is 13 halves. So let's plot those points. So we have 0, 5, -1, 11 halves. Which is 5.5, so right here. Then we have -4, 6, and we have -9, 13 halves, which is 6.5, so right here. So again, we need to make sure we're connecting our dots in the right way. So here's our parent function. So this point became this point. So this is my new starting point, and then it travels to this point, which became this point. So my graph is actually going to now travel to the left. The reason why that's happening is because of that reflection over the y-axis. So instead of traveling over to the right, it's going to travel over to the left, then you can see it's been shifted up 5, definitely. And it is a little bit flatter than the parent function. It's not growing vertically as fast, so that's that vertical shrink. So you do need to make sure that you not only have the correct coordinates, but that you're connecting them in the right way. It'd be really easy to start here and go down this way, and you would have the wrong graph. So make sure you kind of align. You can say, okay, this point became this point. This point became this point. This point became this point. So you connect them in the right order. Now for our domain, remember we always go lowest x value to highest x value. So it's going to go to the left forever. So our lowest x value is in negative infinity. The highest x value is 0. And then for the range, the lowest y value is 5, and it will keep increasing forever. So it's 5 to infinity. I know this graph looks like it's flattening out, and it does flatten, but it will never become perfectly flat. It will keep increasing. It will just do it really slowly. All right, so now I'm going to have you pause the video and give this one a try on your own. All right, go ahead and check your work here. We do have 4 transformations: a reflection over the x-axis, which is vertical, vertical stretched by a factor of 3, horizontal translation left 7, and a vertical translation up 2. So here's my parent function coordinates, here's my rules, so x minus 7, and then negative 3y plus 2, the y values for my parent function. So my graph goes from looking like this, the reflection makes it decreasing, and then I can see I'm shifted left 7 up 2, and it is pretty stretched out because of that vertical stretch by a factor of 3. All right, so now let's try a cube root function. So let's describe the transformations. First, it's the same as with the square root function. This negative out front is a vertical reflection, which is a reflection over the x-axis, but it will affect the y values because it's vertical. This is affecting the x values grouped with x. So this is a horizontal translation, and it's going to go to the right 1 unit. It goes in the opposite direction for x. And this one is vertical. It's not done specifically to x. It's outside of the cube root. I'm subtracting, so it's a translation, and then we go down 4. So notice that this time our parent function is the cube root function. So I picked different x values for my t-chart. So here's my parent function coordinates. And then the rules, we make them in the same way. So the only horizontal change I see is to the right 1. So I'm going to add 1 to all the x values. Maybe we do that first this time. So we have negative 7, 0, 1, 2, and 9. And then for the y values, I'm going to multiply them by negative 1 for the reflection, and then subtract 4. So negative 2 times negative 1 is 2. Positive 2 minus 4 is negative 2. Negative 1 times negative 1 is positive 1, minus 4 is negative 3. 0 minus 4 is negative 4. Negative 1 minus 4 is negative 5, and negative 2 minus 4 is negative 6. So let's plot those points. So we have negative 7, negative 2. We have 0, negative 3. 1, negative 4, 2, negative 5, and 9, negative 6. So remember, our parent function graph looks something like this. I'm only going to plot part of it. So that reflection over the x-axis, instead of increasing, it's going to be a decreasing graph, and then it's shifted down to the right 1. So it looks something like this instead. So there's our function. And for these, domain and range should be super easy because they are both always all real numbers. So that's kind of autopilot right there. All right, let's try this last one together, and then you have one last you try. So here I see we have that 3, it's out front, which makes it a vertical stretch by a factor of 3. And then here, be really careful. I'm multiplying to x. So it's going to be a horizontal stretch or shrink. But think about what the factor is first. The factor is the reciprocal. So since the factor is 2, it's also going to be a stretch. So I have a horizontal stretch by a factor of 2. And then here, I have a vertical, because it's outside the cube root, a translation, because I'm adding, and then it goes up 2. And again, our parent function is the cube root function. All right, so let's fill out the parent function coordinates. We have -2, -1, 0, 1, 2. And then for the rules, be careful with our horizontal rule. I know this is 1/2 x in the equation, but it's actually a horizontal stretch by a factor of 2. So we're actually going to multiply our x values by 2. And then for the y values, we're going to multiply them by 3 for the vertical stretch, and then we're going to add 2 for the vertical translation. So this one becomes -16, -2, 0, 2, 16. So some of these points will go a little bit off our graph, and so we can just either omit them, we could always change the scale of our graph, or we could just kind of estimate where they would be. And then for the y values, here we have -6 plus 2, which would be -4. Here we have -1 times 3, so -3 plus 2, which is -1. And then we'll have 0 plus 2, which is 2, 3 plus 2, which is 5, and 6 plus 2, which is 8. So again, I'll leave off these two coordinates because they would go a little bit off our graph, but we can plot the other ones. So we have -2, -1, 0, 2, and then 2, 5. And then we know that our graph should make this general shape. It should look like that cube root graph. Again, if you remember what the parent function looks like, it looks something like this. So we are going to want to make sure that it has that same general shape, like it's growing a little wider than it is up and down. We don't want it to end up looking like a cubic function. We want to make sure it looks like that cube root function. And then for domain and range, we know that these are always the easiest ones because they're both all real numbers. All right, here's the last you try for this video, so please pause the video and give it a shot. All right, go ahead and check your work here. So here's the descriptions of the 3 transformations. I have my parent function coordinates and the rules, so it's going to be x minus 3 to shift to left 3, and then 2 times the y values minus 4. So your graph ends up looking something like this, and the domain and range are both all real numbers. All right, that's all for today's video. Thank you so much for watching.